today's tutorial we will talk about Siamese neural networks. So, Siamese neural networks are generally used to tell us how similar two images are. So, for example, after training the neural network, given a completely new image, the network could then compare the image to an image from each of the categories and determine which category is the most similar to the given image. So, for example, the category could be a person and we input an image of a different person. The neural network will tell us the similarity between them. So, to better understand this, let's look at this example here. We have the two inputs, x1 and x2, and we pass them through convolutions, poolings, and fully connected layers to get a feature vector. And this feature vector is just an encoding of the images. So to build a face recognition system, we need to compare these two images. So we pass in the x1 image, we get a feature vector of 128 numbers, let's say, and we pass in the second image x2 into the same network, and we obtain a different 128 vector, simply said, a different encoding. And after we acquire these two different vectors, we want to calculate the distance d between them. So to see how similar these two images are. The idea of getting two vectors from the same network and comparing them is called a Siamese neural network architecture. So, we want to train the neural network in such a way that the encoding that it outputs results in a function d. This will tell us when two pictures are of the same person. The parameters of the neural network define an encoding, for example f of xi. So for this image xi, the output is the encoding f of x1. So the output is a 128 encoded vector. We want to learn the parameters so that if two pictures xi and xj are of the same person, then the distance or the difference between them should be small. And in contrast, if xi and xj are of different persons, then the difference or the distance should be large. So let's look at the architecture here of how the network works. So we have two images, input 1 and input 2, and we have two identical neural networks, so we will call them sister network 1, sister network 2, and they have the same weights. And the last layer of the neural network is fed into a contrastive loss function, which calculates the similarity between the two images. So, the object of the Siamese network is not to classify, but rather to differentiate between the images. So a loss function like a cross entropy loss is not suitable for this problem. The contrastive loss function evaluates how well the network distinguishes a given pair of images. So the function can be written as this over here on the right. This may all sound pretty confusing. How can we only pass two images into the network and how can we train it that way? But when we go into the coding part, it will all make sense. So the dataset that we will be using is the so-called AT&T dataset, and it consists of 400 samples of the size 92 times 112, and it has around 40 people in it, 40 different people, and they are in different head poses, and they have around 10 images each. So we will use this dataset for the training. So for the coding part here, I have inputted a dataset that you can find on our GitHub. I will leave the link down in the description, so I didn't load it in, so I'll just push it inside, so it's data.zip. And while it's uploading, we will check the code. So here I have inputted all the necessary libraries that we will be using. So some of them are the regular ones like matplotlib, numpy, random, pill, and so on. And also I have inputted the torch libraries that we will be using like torch vision and torch. Moving down, I have created some helper functions like the imShow function that we will be using for showing plots, and the showPlot function that we will be using to show different plots like the loss plot, accuracy, and so on. And here we can see the Siamese network dataset. So, one interesting thing about the Siamese neural network, is that it accepts two images as input. So we need one image that we will be comparing with the second image. And we also need a label. This label will indicate if the two images are from the same person, or let's say the same category. Like if it's a cat in the first image and if it's a cat in the second image, we will say that they are similar, so we will set the label to be 0. If they are not the same, for example, we have a dog and a cat, we will set the label to be 1. So to indicate that they are not the same category. And here I'm just doing that, so I'm selecting approximately 50% of the images to be in the same class. So I'm just doing that here. I will not go in any details here. You will find the code on the GitHub, so you can download it and you can analyze it. But simply I'm opening two images with the pills function image dot open, and also I'm transforming it, and then I'm returning the first image and the second image, and then I'm simply returning if they are belonging to the same category. So if it's of the same person in this example here. Now I can just simply run this code, and this one over here. And for the dataset, it should be uploaded by now. Yeah, it's uploaded. So simply I am only unzipping it. This is just for caution. I'm just deleting, if any folders are named data, I'm just deleting them. And if I run this, it should just unzip the folder like this. And if you take a look at the dataset, here we have a testing and training folder. In the training folder, we can see some subjects. So for example, the subject 1, he has 10 images and they are of the format PGM. And testing, we have 3 subjects, 5, 6 and 7, and they also have around 10 images. Now that we have loaded or unzipped this data folder, we can then load it in using the image folder. We're just passing in the training folder, the location of the training folder, and we will just load it in. For the transformation, we are resizing our images to be 100 times 100, and we are transforming them to tensors. And then down here, simply by using the Siamese network dataset class that we created up here, we're just passing in the folder dataset that will just pass in the directory where the images are, or the location, and we are passing in this transformation. So by running this, it should load our dataset. And down here, I'm just creating some visualizations. Let me run this again. So I'm creating a data loader for this dataset that I loaded in up here. I'm shuffling it and I'm setting the batch size to 8 so that when we extract one batch like this, we will get 8 images. So as I mentioned before, this example batch here, the first batch in our data loader, consists of 8 images and another 8 images and a label. So if you look here, we have example batch 0. This is the first pair of 8 images. And we have example batch 1. This is the second pair of 8 images. And I'm just showing them here using the helper function that we created in the beginning. And I'm just making a grid. So I'm concatenating them like this. And then down here I'm just printing out example batch of 2. And 2 here indicates the label. So I can just zoom in here. So we can see here this person and this person are not the same, so it is 1. This and this not the same, so 1. Similar here, this is 1, and if it's the same person, like this example here, then the label is 0. Same thing here, they are of the same person, so the label is 0. This is not the same person, this is not the same person, so 1 and 1. And the last person is the same in both images, so the label is 0. And this is the structure of our dataset, or how we will load them into the training and use them. Now that we have seen how the dataset looks like and how we are retrieving the data, we can now move on and see the Siamese neural network architecture in more detail. So here, in this image, we can see that we have two identical neural networks. So the top one up here and the bottom one are identical. So we first have our input image, then there are three convolutions combined with max poolings, and then the output of the third convolution goes into a fully connected layer, and then in another one, and the output are two numbers. Then those two numbers in both of them, so we have one neural network on one image and the second one on the second image, the outputs then go into the contrastive loss function. So when we move on to the coding part, it will be more easy to understand than in these images here. So let's scroll down and look at the Siamese network class. So here I have created two sequential layers. The first one is the convolutional layer, and the second one is the fully connected layer. So the convolutional layer, I will just zoom in here. The convolutional layer here has the same architecture as up here. So we have first, the input is one-dimensional, so it's a grayscale image, and it outputs 96. The kernel size is set to 11 and the stride is set to 4. So the same as here on this diagram, let's say. Then we apply the value activation function and then max pooling. So this is done 3 times. So again, 96 as input, output 256. Now the kernel size is 5 and the stride is 1. Then a activation function and max pooling. And the last convolutional layer accepts 256, outputs 384, and we are just doing the activation, so the value function. And then we have a fully connected layer, or a sequential fully connected layers. So here we see that we have an input of 384 and it outputs 1024 numbers, or this is a vector of 1024 numbers. Then we apply an activation function. Again, it accepts 1024, outputs 256, activation, and the last layer, it accepts 256 and outputs 2. So how do we apply this? Well, when we call our model on the images, PyTorch works in the following way. So it sees this forward function, and once we do something like model and we pass in the image, it goes automatically in this forward function. So here we have set that our input, we have two inputs, input 1, input 2, so this is the first image and the second image, and then down here we call the forward ones function for the image 1, image 2. So the forward ones function up here is just the regular forward pass. So we apply first convolutions, we flatten our image or the output of the convolutions, and then we pass those outputs into the fully connected layer and we return them. So down here we get the output for one image and the output for the second image, and we just return them out of the model. So we can just run this. Now we can move on and look at our loss functions. So here I have an example. This formula up here is the formula or equation for the contrastive loss function. So it goes like this. So we take 1 and we subtract the y. So y here represents the label. As we mentioned before, the label is either 0 or 1. If the label is 0, that means that the two images are of the same category or the same class. So for example here, these two images are of the same category and they would have a label of 0. And if the label is 1, for example these two, so this is a 7 and a 1, so the label would be 1, so they are not of the same category or class. Now we subtract this, we take the mean of the Euclidean distance, so d of w here is the Euclidean distance, and then we set it to the power of 2. Then in the second part of the equation we add the label and we take the mean again of the maximum of 0, and this m here represents a margin. So in the code that we will go over later, we set the margin to be 2, so a constant. So we're taking, if the margin subtract the Euclidean distance is less than 0, we set it to be 0, and we set it to power of 2. So, if you take a look at these examples here, if we process these two images into our model and we get the output, we pass that output into the formula here. We get a distance of 0.59, which is a high distance, and it indicates that these two images here are not the same. If the distance is small, like these two, so these are of the same class, just different images, we can see the distance is very low. And as well as here, the distance is low, and if the images are different, the distance is big. So looking at the code down here, we can see our contrastive loss function. I have created a class. I set the margin, as I mentioned before, to be a constant of 2. It is a parameter, but I set it to be 2. And this part is the most important part. So we have our forward function in the loss. So we're passing in the output from the model for image 1, output of the model for image 2, and a label. Then we calculate the Euclidean distance using the pairwise distance function. We pass in the output 1, output 2, so the output from the models. And then down here we have our loss, contrastive loss, which is this formula up here transformed into Python code. So, where do we use this? Well, we first need to load our dataset. We load in the Siamese dataset, we shuffle it, we set the number of workers to 8 for faster execution, and the batch size we will set it to 64. I will just run this piece of code. And down here, in this part, we are just calling our model, the Siamese network. We are sending it to CUDA or GPU, and up here, for the criterion, we are now using contrastive loss. So the class that we created up here. Earlier here we would set, for example, to be cross entropy loss or something like that, but cross entropy wouldn't be of much of a use here, so we are using the contrastive loss function that we talked about earlier. And for the optimizer we're using the standard add-on optimizer, optimizing the model, and the learning rate I have set to be a low value of 0.005. Now that we have initialized everything and our model and loss are done, we can now see this diagram here of the flow, how the Siamese neural network works. So again, we have two images. We pass them into the sister or Siamese neural networks here, which have the same weights. We then pass the outputs from the models into the contrastive loss function that we created, and we get an output. The output is the distance, or how similar or dissimilar the two images are. So moving down here we have our training. I'm saving a counter, so this is just for visualization later. I'm saving the loss and also the iteration number. So we are iterating through all the epochs. I have set 100 epochs. We are iterating over all of the batches. So remember, the data loader now contains two images, so image 0 and image 1, and also the label. So earlier we would have something like this, just one image and one label. Now we have two images and labels. Then down here I'm sending everything to CUDA or GPU. I'm setting the gradients to 0 of the optimizer, and I am passing the two images into the neural network. So we obtain output 1 and output 2, and looking at the image here, output 1 and output 2, and the next step is passing them into the loss function. So down here I am passing the first output and the second output and also the label. Label is indicating 0 if the images are of the same category and 1 if they are not of the same category. After this we get our loss and we just do the backpropagation. After that we can then optimize. We are optimizing our optimizer, so just by calling .step on the optimizer. And then every 10 batches I want to print out some metrics so I can see how my model is performing. And down here I'm printing out the epoch and also the loss. And then I'm adding to the iteration number plus equals 10 because I am printing every 10 batches. And down here I am appending to my counter the iteration number, which is going 10, 20, 30, 40 and so on. And also I'm saving the loss. And down here I'm just showing the plot or just plotting it by passing in the counter, which is a list, and also the loss history, which is also a list. and then we can just run this piece of code here. Now this training should be pretty quick, so now if you check out the loss, we can see it gets to a number pretty close to 0. So also we can see the loss here, so I have plotted the loss, so we can see here that it started at 2 point something, got up at 2.5, then dropped down until it converged, let's say, around here. So we can say that it has trained successfully, so I'll just close this view. And in this piece of code here, I'm just finding the dataset, the test dataset. I'm creating my Siamese network dataset from this testing dataset. I'm also applying the same transformations, and then I'm just loading it in as the test data loader. Then down here, I'm just taking out one image, so I'm creating a data iter new object, which is iter of the test loader, and I'm just taking out the first batch or the first image, because our batch size is 1, so this will just be one image, x0. Then I'm iterating 10 times and I'm extracting the next 10 images in this data loader. Down here I'm concatenating the two images, so they will be horizontally stacked, each one to the other. And down here I am getting the output from the trained model, so just by calling net or the network, passing in x0, x1, the two images, and here down here I'm just calculating the Euclidean distance. So not the contrastive loss function, just the Euclidean distance, by using the pairwise distance function from the functional in torch.nn. Pass in the first output and the second one, and I get a value down here which is indicating the dissimilarity between the two images. So I will just run this. And down here, so we are comparing the left image to the right image. We can see here that the similarity is around 2, but when the two images are almost identical, like this here, so this is the same person, the similarity is 0, because they are almost identical. So this is a great example. Down here, these two faces are not of the same person, so the similarity is big, 4.09, and here 2.03, because they are not the same. And going down, this image here, so it's the same person, so that this similarity is 0, which is a great result. Going down, this is the same person, so it's 0.01, so it's not 0 but 0.01, because of the head position and angle. And these two are not the same, and these are not the same also, so they have big values. So we can say that our model learned how to distinguish between faces. Now that would be all for this tutorial. I hope that you liked it and you found it useful. Now I think that you understand the basic concept behind the Siamese Neural Networks architecture and how it works, the contrastive loss, and so on. So now you can experiment, and instead of the AT&T dataset of the faces, you can try something else. For example, the Siamese neural networks are used to distinguish between numbers and characters. So you can, for example, use the omniglot dataset or the MNIST dataset, MNIST fashion, and so on. Thank you for watching, and be safe.